Hello everyone, my name is Caleb Dowell, and today I will be talking about my RCEU project classifying Aurora Borealis from human eyes to machine vision. We all love the Aurora and are very familiar with the very bright, colorful pictures that we see of it, and in many ways they seem almost supernatural to us, but in fact there's a very scientific explanation to how they are created, and the Aurora gives very strong implications for what is happening in space and how the Earth defends itself from harmful solar weather. Now, to begin this explanation, we first have to explain the Earth's magnetic field. Due to a liquid iron core, the Earth turns itself into a very, very big magnet with a magnetic field. This picture you see shows what the magnetic field looks like without any form of solar weather affecting its shape. The yellow lines you see represents the path a magnetic object would take once it is close enough to the Earth due to the Earth's magnetic force. The flow of matter from the sun is often referred to as solar wind, aptly named because of the very wind-like nature of these particles. Now, these particles consist primarily of electrons and protons ejected from the expansion of the sun's atmosphere due to very, very immense heat. Because these particles have a magnetic charge, they pull the sun's magnetic field with them, and once they reach Earth, the two magnetic fields of the sun and the Earth, along with all of these particles, interact with each other in a very, very violent and very complex way that I won't go into great detail. But the important thing to remember is that the solar wind interacts with the Earth's magnetic field, compressing the sunward side of the magnetic field, and then extending the spaceward side of it. The flow of these particles around the Earth look very similar to how water would flow around a boulder in a raging river. Now, the Earth's magnetic field shields us from most solar wind. However, due to the shape of the magnetic field, some particles are able to penetrate deeper and are directed towards the poles. Once they reach the atmosphere, these particles interact with oxygen and nitrogen to emit light, and that light turns into what we know as the aurora. Now, to help us understand this interaction better, this is an animation of how the Earth's magnetic field stretches and warps. The dark circle you see is the Earth. All of the colors represent the density of solar wind, with red being more dense, and the lines you see being the Earth's magnetic field. The details here aren't super important. It's just a visual to help you understand that the magnetic field is constantly in motion and is constantly affected by how strong the solar wind is. Now, even though most solar wind is redirected away from the Earth, the most powerful solar ejections can damage our technology. In 1989, there was actually an ejection that caused a blackout across the entirety of Quebec, Canada. In this article, it states that it took only a matter of minutes for this ejection to reach Earth. These ejections can happen at any time, and we have very little time to react when they do. So this leads us into the motivation for our project. It is of great importance to better understand how the Earth interacts with solar weather and to better identify patterns to predict future events, to avoid these blackouts and further damage to our electrical infrastructure. Now, to achieve this, our project incorporates machine learning with auroral science. Machine learning will be able to catalog images of the northern sky quickly and easily to find patterns and predictions in solar weather. We catalog these images from the Themis array of ground-based cameras, which I will discuss in just a sec, to classify and label different sky conditions, whether it's cloudy, a clear sky, or a clear aurora, so on and so forth, to train this machine to identify different sky conditions. So the Themis array of ground-based cameras is a current project that has set up 21 cameras across the northern hemisphere. The map you see there shows the location of all of these cameras, with the circle around them being their approximate field of view. The image on the left shows what this camera looks like. Inside it is a camera with a fisheye lens to take a picture of the entire 360 degrees of the night sky. These cameras will take a picture every 3 seconds of every night, creating hundreds of pictures every single day, and will produce millions of images in the foreseeable future. Now, these pictures are posted on a public website that can be accessed by anybody. This is a screenshot of the website. On the left you can see are the list of stations. On the top left you can see the day's date. Next to all the stations you see all those circles are individual images taken every hour. You can click on one of those images to get an expanded view on the right of every minute, and you can click on any of those minutes to see every 3 seconds. Again, like I said, this website is open to the public, and I have a link at the bottom if you want to go to that website to visit it. Now, our team actually made software to reorient these images from fisheye to normal and compile them into a video. This one here is one of my personal favorites. This is a view as though you were looking down from space at this aurora. All of the white lines you see are geomagnetic coordinates, and the blue line you see moving across is geomagnetic midnight. Making these videos are very helpful in seeing these images over time and are much better and are very useful in helping us classify these images over a period of time. So after analysis of 6 stations over 6 months, I classified many types of different sky conditions, but these are 9 of the most basic and most common conditions. There are 2 main types of auroras that I looked at, which are structured and diffuse. Structured auroras are the auroras we see in all the pictures, very bright, very colorful, and have very, very distinct borders and edges. Diffuse auroras aren't quite as bright and have softer edges, but are still a very distinct aurora. As far as interference, there are 2 types of cloud interference, the first of which is cloud cover, which has one monotone color, while there is also basic clouds, which are patchy and don't quite cover the entire sky. There are a handful of forms of light interference, the most common of which is from the moon, which you can see in number 5. There are even cases of having a completely clear sky with no aurora, no activity, no light, which is in number 6, and I labeled that as no activity. You can see the difference between that and others because you can see a lot of stars in the image. There are even cases of snow covering the camera, and even cases where the camera has a technology error, where the picture is warped, or even an inactive camera. You can see a picture error in number 8. Number 9 is the combination of cloud cover and light. The reason I added that is because cloud cover and light is the most common form of interference, so I wanted to showcase an example of that as well. So here's a final chart that I made with the total of all individual classifications. The numbers here aren't really that important, but I will show a visual of all of the data in the next slide. But I wanted to showcase the 16 different categories and the 6 different months that I chose. As you can see, the base characteristics are light, clouds and cloud cover, snow, no activity, so on and so forth, and then combinations of all of those. For example, you could have a picture with half of it covered by snow, the other half of it covered by clouds. There may even be a moon out behind the clouds. There can be a lot of different combinations, and some of them occurring much more often than others. Here's a visual, like I said, of that data shown in the previous slide. The 2 green wedges on the top right are the usable images. If you combine those together, you get a usable image about 20% of the time. The most common forms of interference, like I said, are cloud cover and light, followed by light and clouds, and then light on its own, so on and so forth. You can pause the video if you want to look at the data further if you would like. So in conclusion, this project was specifically done to find patterns in aurora activity to avoid possible damage to electrical systems on and around the Earth. I surveyed 6 stations over 6 months in various phases of the solar cycle. I cataloged these images and found that there was a present and clear aurora about 20% of the time, with the most common forms of interference being clouds and light. This process took me all summer to do, but a machine could do it much, much faster and can continue to catalog these pictures as time goes on, all on its own. Thank you all so much for listening. I hope you all are staying safe. Thank you so much.